All right, folks, welcome to lecture 2 in the series on generative adversarial networks. I hope most of you have already watched Monday's lecture, and if you have, you've learned to appreciate the beauty of the whole concept. Anyway, I'll hand over to Ben to finish the second part of the series, and we'll learn more about the subject. Right.
Hello, class here and online. We're going to talk about generative adversarial networks, or follow up on them. Let me just pull this up for a second. Okay, so part 2 in our series, we're going to do a little recap of what we talked about last time. Then we're going to talk about what the optimization issues are and kind of the core problems that we have. And then we're going to go through some techniques people have done to make things better, make things more stable. So, to start with, so far we talked about what a GAN is, how it works, and what kind of problems you can use a GAN for. A GAN is you're trying to train a generator, and you're trying to make the generator produce samples from a target distribution, and you have the second player, which is the discriminator, which is trying to guide the generator and tell it what to do, help make it better. The generator and the discriminator are trained adversarially. How do they work in theory? The discriminator is actually calculating a divergence between the generated distribution and the target distribution, and the generator is trying to minimize that divergence. By minimizing the divergence, the generator is going to produce a distribution which is similar to the target distribution you want it to produce. A little bit of pseudocode, but you guys will probably have a recitation and stuff to go into more detail. But the basic idea is you define one network, which is your generator. It goes from random inputs. It produces an image. You define another network, which is your discriminator, which goes from images to a scalar. So whatever MLP CNN you want to have that fits that description can work. And then the actual training method is just you're drawing a sample from your prior, which might be a Gaussian. You draw a sample from your data, which is 32 images. And you do gradient descent on the generator with respect to the generator loss, and gradient descent on the discriminator weights with the discriminator loss. So you need to make 2 optimizers, however you do that in your framework, and you need to do gradient descent on the 2 separate sets of weights separately. What kind of problems can we use GANs for? We talked about that last time. We're not going to get into too much detail this time, but it's not just generating a distribution. You can generate conditional distributions. You can do clustering. You can do translation. You can do semi-supervised learning. Basically anything where you have a discriminative network you could have used traditionally, you can now use a GAN. You can use GANs for generating auxiliary data sets, for example. If you can use a GAN to generate pairs of X and Y, then now you can generate those examples and train your data set on, or train your model on basically an infinite data set. So data augmentation is another interesting usage of GANs. So there are a lot of things you can apply it to, but we're going to talk about the core GAN together. It's a powerful tool. It's got a lot of potential, but the problem and the concerns have been the evaluation, which we talked about last time, and the actual pragmatic issues of how you get them to train, how you get them to converge. And that's what we're really going to focus on today. So with that, we're going to talk about the optimization issues and then how we solve them. So, GAN training can be a little tricky to diagnose. You have to kind of get used to it to some extent, and seeing different things that happen. Let me see if I can get that to open correctly. So one frequent problem with GANs is called mode collapse. And what happens is you're trying to learn a distribution like the numbers 1 through 10, and you train a model on the numbers 1 through 10, but you see that as you're training it, it's really likes 1s, 3s, and 8s. But it's not really doing other numbers. And then maybe as you train it for a little bit longer, it goes and it only produces 1s. So it produces a wide variety of 1s, but it doesn't actually cover the entire space you wanted it to cover. This is one particular type of issue, which is very common. It's called mode collapse, and you'll see it a lot in the literature. But not all failures are really easy to describe. This is a video I found online from someone else's attempts to train DC GAN, but I've seen similar results. But basically, if you train it and the parameters aren't quite right, this might be your output. And I don't know if you guys know what CFAR is supposed to look like, but it's pictures of trains and dogs and fire hydrants and stuff like that. So this is clearly not doing what it's supposed to be doing, but the point being that sometimes your GANs can give you these weird, however you might want to describe what's going on right now, but it never quite hits the good purpose. It looks like ink blots or something. And the real question is, how do you avoid those issues? Sometimes it's unclear what's going on. Maybe your discriminator is doing too much. Your discriminator network is too big with too high a learning rate. Maybe its discriminator is not complicated enough. Maybe it's too weak. Maybe it's not training fast enough. And you really have to understand a lot of your metrics. You really have to look at the data, look at the images it's producing to try to troubleshoot what the problems are. So the techniques we're talking about try to alleviate the issue and try to make it less sensitive to hyperparameters. But no matter what, GANs are very sensitive to hyperparameters. You train an MNIST data set, you're going to get a 90-something no matter what your hidden dim is. It might be a little better, it might be a little worse if you had some batch norm, but it's not going to make a huge difference. Versus with GANs, things like batch norm and regularization can make something work or not work, not just simply be a little bit better. So why do we have these optimization issues? At the core, it's because we have simultaneous updates. We've got two different players, and those players need to be in some sort of balance. And you can't have one guy beating the other guy up entirely, whether it's the generator or the discriminator. Also, in general, two-player games are not guaranteed to converge no matter what, even in very simple cases. We'll also talk about the fact there's a stationary point, but whether you reach it and under what conditions you'll reach it. And just in general, it's a harder problem and it's not as fully studied.
Is this a zero-sum game or no?
It depends on which GAN you're working on. Like there's a later one we talk about, which is WGAN, which is a zero-sum game. Mm-hmm. This original version of the GAN, like each player has their loss is a cross entropy loss, so the sum can be infinite and like really weird numbers, just because that's what logs do. But overall, the point being, like they can't both be winning. Mm-hmm. So I guess in that sense, roughly, okay. It doesn't come out to actually be zero in a lot of the equations, but the point of we will want to encourage them to both work together, and there actually is a model we'll talk about later, which is called consensus optimization, which is trying to say like, hey, maybe there's a goal you guys can both work to at the same time, but at the core, they're diametrically opposed. Because one guy wants to say, this is real, this is fake, and the other guy wants him to be wrong.
Yeah.
So either you're right or you're wrong.
I mean, it's kind of like zero-sum game where like,
yeah.
if the discriminator wins, that means the generators lose.
Right, yeah. It's just like, I don't know if you would literally call it a zero-sum game if it's not literally not zero, but in terms of what's going on. In some formulations, it actually does work out to the total loss is zero and one's positive. So we'll see the cleaner versions later. But as to why we need the simultaneous updates, an interesting question I've actually gotten before is why can't you just like train the discriminator and have a really good discriminator, then use that discriminator for everything? The problem is that for any given discriminator, if you just hold the discriminator flat, let's say your discriminator is giving mostly 0.5s for everything and there's one part of the space where it's slightly higher, the best generator for that discriminator is to put all of the mass on that point in the discriminator. So the discriminator is saying what's real and what's fake. There is something in that space that is the image that the discriminator thinks is the least fake, the most real image. And the best thing for the generator to do would be to only produce that one good image with 100% probability, and it would get the lowest loss. But clearly that's not what you want. And the other problem is that the optimal discriminator, when you converge training, it's emitting a 0.5 for all inputs. It's a flat distribution that it's learning. So clearly, if you've got a flat distribution, you can't be using that during training. So you really can't just have a discriminator that works for everybody. The best discriminator is something that happens as you're generating, as you're training. The best discriminator depends on what the current generator is, so you do have to do them back and forth. By the same kind of token, you can't train the generator first for obvious reasons because the generator is trying to learn from the discriminator. So you can't do one and then do the other. You really have to do them in some sort of parallel, alternating sort of fashion. So I talked a little bit about balance. What affects this balance, which is kind of a an abstract term we're using, but just a sense of which player's beating the other, which player's learning more than the other. Is if the discriminator is really, really good, then there's nothing the generator can do to confuse it. It has no hope. There's nothing it can do. If the discriminator is really, really bad compared to the generator, then the generator could be producing junk, and the discriminator still can't tell the difference, so now you're not getting good data. Your discriminator has to be good enough that it can guide the generator in some meaningful way and not just push it in some general direction. So the things that affect the balance are things like what optimizer you're using. What are the learning rates of the optimizer? You've got one optimizer for your generator. You've got one optimizer for your discriminator. They can have different learning rates, different styles, etc. You have to look at the architecture, the depth, the number of parameters. If your discriminator is a 2-layer MLP and your generator is like a ResNet with 150 layers, that's going to affect where you get to. You do want to have some sort of balance. Maybe it should be 100 layers in the generator and 75 in the discriminator. What it actually works out to is an experimental question. Another big factor is regularization. We will talk about some experiments and specific types of regularization people have done, but in general, regularization makes a big impact. Regularization affects whether something overtrains, whether it undertrains. Regularization affects how quickly things train. Also, things like batch normalization affect how quickly things train. If you put batch normalization into your generator, suddenly your generator converges much, much faster, and if your discriminator stays the same, you've suddenly put the whole system out of whack. Important thing to note is how people actually do the training. You can do what are actually called simultaneous updates, where you literally update one and the other at the same time with the same parameters and try to let them step at the same time. But it's actually more common to do one and then do the other, then do one and do the other. You might think, just naively, let's do one and the other, one and the other, one and the other, one of each. But actually, you could do this one 3 times, then this one time. So that's another way that people affect the balance. Commonly, you'll do your discriminator more times than your generator, sometimes at a lower rate, because you want your discriminator to kind of be a little bit ahead of the generator. So depending on the paper, maybe you train the discriminator 3 times, and then you train the generator once, or maybe 5 times, something in that range. And again, that's all experimental and just depends on what you're working with. Another idea people have had is trying a dynamic number of iterations. So maybe there's some sort of metric you can run to see how far ahead the discriminator is and how far ahead the generator is, and maybe you train the discriminator extra if it's behind. Things you can use are like the loss and how accurate it is. So if the discriminator is getting less than 50% correct, meaning it's saying 60% of the time real images are fake images and fake images are real images, then you probably don't want to use that discriminator. So you can look at certain factors like that and say, maybe I'm going to train my discriminator until at least it gets that accuracy before I use it on the generator at all, and try to keep that balance. So what does that actually look like? Here's a very simple generator or GAN that I made. This was early on. I was trying to explain what a GAN is to one of my professors, and this is the simplest GAN you can do. The target you're trying to match is a single 2D point. It's just a point mass. That's all we're trying to make. Your generator outputs a point mass, and your discriminator is a linear function. It's not an MLP or anything. It's literally, a times a weight vector plus a bias. So it's got 3 parameters, 1 for each dimension plus a bias. And what this actually looks like, and I'll pause because it might go a little fast. So we've got 1 point, which is the blue point. The blue point is what you're generating. The green point is where you're trying to get it there. But the way you get there is there's this linear function, which is the colored background. So what you see is the colored background is a function you're learning, which is trying to push the blue dot towards the green dot. And I think this is kind of a very high-level, simplest GAN. If you can understand how that works, then you can understand the rest of it. So this is basically what GAN training looks like. You've got a gradient. The gradient is trained by a neural network, and that gradient tells the generator which direction it should go, how it should move. And eventually, it might oscillate back and forth, and when you're done and everything converges, if you actually look at the colors, you'll see that it's about 0.5. So That's what you want in your simplest GAN, moving things back and forth. But you see, even in a very simple GAN, if the generator is approaching the point, it'll overshoot, and then the discriminator needs to go to a different direction and push it back in a different direction. It might converge, it might not converge. That all depends on your hyperparameters and things like that. Another important point to make that I mentioned earlier is going to a higher level of just two-player games. Very simple games even will not converge using alternating updates. Even when there's a simple game, there's a simple optimum, it's obvious when that optimum is. If each player just gradient descends, it might not go to where you want it to go. So one of the simplest examples we're able to get, which is rock, paper, scissors. There are three options. Everyone knows the game, hopefully. But if you were to imagine you initialize these players and they're randomly playing rock, paper, scissors, let's say player A is preferring rock, and that means player B should start playing paper. If player B is playing paper, then player A should play scissors. If player A is playing scissors, player B should play rock. So you can actually write that out as a, if you write out the equations of the probability of winning and losing, you can perform gradient descent on that. So a very simple experiment is you can write the equation for how much each player is going to lose. Your expected win rate is the probability of A playing rock times the probability of B playing stone, or playing scissors, right? Or the probability, and you know, it's adding the probability of all the combinations where E wins. So if you write out the combinations, you can just do gradient descent on your probabilities of playing each of them, and each player should go down to, you know, finding the optimum, you would hope. But what we'll see is that you actually don't get to the optimum. So if you randomly play rock, paper, scissors, there's a very obvious global optimum, which is you equally play each of the three. Because rock, paper, scissors is completely random, and you shouldn't prefer anything. And if there was a player that preferred one or the other, then you could beat that player. But if the only strategy you can't beat in rock, paper, scissors is complete randomness. That's all we're trying to say. But what we'll see is that it's an unstable optimum. And the reason it's unstable is that if one player is slightly off from the optimum, then the optimum for the other player is all the way at the end. And a good example of that is, let's say we've got a player B. Player B plays rock with 40% and then 30% for the other two, right? So if he plays 33% all the time, then the best you could do against him is 33% win, 33% lose, 33% draw. If the player B plays 40% rock and you were to play evenly, then you would get even, you know, 33% for everything. If you were to play paper with 100% probability, then you would have a 40% chance of winning. And if you were to play paper with anything less than 100% probability, you would have less than a 40% chance of winning. So there's a situation where we see that, yes, the optimum for both players is 30%, or, you know, a third for each of them. Both players play a third, the gradients are zero, they're both at a global optimum, we're at a stable system. We're at a stationary point in the system, and that works. But if even one of them is slightly off, then the other one wants to go 100% into what beats it. And that causes a set of oscillations. And if you actually do gradient descent, it looks like what I kind of just described, which is you actually see, there's more text than I thought there was. Yeah. You see a silly thing that happens, but they never end up converging. You have this player's playing rock, and because this player's playing rock, this player is going to start playing scissors, and then everything's going to start going back and forth. But they end up into a cycle, and you can end up with cycles like these even though you have a stationary point. And that's the part you have to understand. It's not just understanding where is there an optimum, is there an optimum, it's are things near the optimum converging to the optimum, or are things near the optimum going away from the optimum. So that requires an understanding of really what's the vector field surrounding it, what do the gradients look like in a space around the optimum, and are they going towards it or away from it? So that's what we try to say here. Just that stationary doesn't mean it's stable. What we're looking for is a well. That's the language people like to use. If there's kind of like a well or a basin of attraction is another word people like to use, or I guess phrase. But something that's drawing things into that stationary point or not. And what that means is you need to have some degree of smoothness in the discriminator. You have a discriminator, the discriminator says, you give it a generated point, it gives you a 0. You give it a real point, it gives you a 1. What we're really interested in is as you're going from real to generated points, it goes from 0 to 1. And that's not necessarily the case from that first statement. Just the fact that it has 0 here and 1 over there doesn't mean that the gradient is actually pointing in that direction. So we want to regularize or make some assumptions or clean up our discriminator in some way that it not only makes the right assignments, but it has some sort of smooth function going between those assignments that puts things in the right way and doesn't have these noisy gradients that aren't helpful. So there are areas around the discriminator, the real and the fake points that are important. It's not just that it's a 1 at the real points, it needs to be a 1 near the real points as well. So with that understanding of kind of what issues there are and what those issues cause, the kind of problems it cause, we're going to go through what people have done to fix it, basically. There's ongoing research. There's probably no silver bullet. There are a ton of papers, as I said last time. And really, combinations of techniques work well. Gets better every year. This will probably be outdated in no time, but it's just a long list of things people have done, trying to find what's the best option. So what we want to take away from this isn't necessarily one method of training GANs that's better than the other. We want to understand the types of things people have done, how they've done them, what types of research people have done, and the general ideas people have worked with to try to make it better. So we're going to talk a sampling of training techniques, not covering every idea because there are a bunch of them. We only have limited time. Our goal is to understand what kind of types are happening. Some of these things are going to be historical or just interesting or lead up, not necessarily great models by themselves. And I'm definitely not endorsing all of these because we're going to cover 100 things. There's no way you can combine all of them. Some of them are good ideas, some of them aren't, but they really just try to paint the picture of what's going on. So with that, here's our list of things. We're going to just cover some through history and different types of ideas people have tried to understand how these networks work. So with that, the first one, probably one of the more interesting ones, is called unrolled generative adversarial networks. You don't want to optimize the current loss. You're not trying to just get better on the current step. You're trying to get better on future steps. So what you can do is your discriminator is trained by SGD, and given a current point, you do SGD a couple points to see what happens eventually. You can actually do gradient descent through SGD, and instead of optimize how the generator is doing right now, you can optimize how the generator is doing in the future. This is pretty cool.
So you keep unrolling, meaning each point gets visited.
Yeah, you actually do the unrolling. So here's the way the equations are written out, which is theta 0 of D is whatever your discriminator currently says. Theta k of D is just taking the discriminator, do a gradient descent update of the gradient of the loss with respect to, exactly what you expect. It's doing gradient descent. And theta D to the capital K is doing it for K steps, 10, 20, whatever it is. You can actually run the gradient descent in a program with automatic, differentiation and do gradient descent on how well the generator does on that future version of the discriminator. And the future version of the discriminator on the generator theta is actually, you're doing gradient descent through that. So you're not just looking for what's the best now, you're looking for what's the best thing that will produce the best loss in the future.
Is this similar to like Nesterov's? How you take like a gradient step and like one step?
Nesteroff does one. I mean, this step, they actually do like 50, which is kind of crazy, but they were doing it on a small data set. I mean, I guess in spirit, it's kind of similar to like looking ahead and don't make the step yet, kind of look ahead and then make your step based on what's going on in the future.
So
Yes?
is the big win here that we train faster or that we avoid local min?
We train much less faster. We avoid issues like oscillations. We avoid mode collapse, the types of problems. So in terms of computational faster, very much no. Because we're literally performing multiple steps of gradient descent plus gradient descent through those steps of gradient descent to do a single update that would have been, a single update. But in terms of where it gets to, Much better. So you'll kind of see that dichotomy in a lot of these, that there are some methods which you'll see they're like, wow, that's really interesting, that gets you to a really great optimum, but I've got to calculate something that I don't want to have to calculate. And there are some other methods which are a nice balance of the two, and there's no silver bullet. So this is a good example of a method that computationally seems like it could be astronomical if you're trying to do inception and do several steps of gradient descent in inception in memory just to get one thing done, but it does actually provide something. So like, for example, in the, I'm not going to show the video right now, but if you do something like this in the rock, paper, scissors example, this unrolled GAN is just a generic question of how you do multiplayer adversarial optimization. It's actually not really specific to GANs. It's basically just saying if you've got two different players, you could gradient descend on what's currently happening, or you can gradient descend on what's happening in the future. So this is actually kind of something that was adapted from techniques in just optimization, and then was like, hey, this works on GANs too. Yeah, so I mean, it's kind of an interesting idea just in terms of optimizing for the future, but we are going to see more efficient ways to do that, which is actually, I guess, the next slide. But yeah, so keep that in mind in what it's trying to do, both in terms of the intention. The intention is don't be greedy, try to find a place where you do something that's good for you now, but next step it might be even worse. So try to find a stable thing that's going to help you in the future, not just be greedy. Yeah, in terms of diagram, you can take a look at this, but basically you've got several steps of your gradient descent, and the gradients are actually going all the way through the gradient descent. So gradient descent through gradient descent tends to be a little headachy, but it is possible.
This is done only for the discriminator, or is it done also for the generator?
This is actually done for, you unroll the discriminator as you train the generator. Why they don't do both, I'm not really sure, but we'll see that in a couple papers. It seems to be, at least, as reported by these guys and a couple others, that making the generator less greedy against the discriminator helps a lot, but going the other way doesn't seem to be as big of a deal. And in terms of results, you see this is a very simple data set. It's just a ring of, it's just a bunch of dots in a circle, but the top is what happens under their unrolled GAN, and the bottom what happens under a regular GAN. So as to reference before, in terms of actual steps, complexity or whatever, they're counting iterations. They're not counting how long each iteration took, which definitely helps their results. But what you see is if you're doing a GAN, it might make a dot on one of those dots, and that one dot might move somewhere else, but the modes collapse, and then that one collapsed mode cycles through all the others. So you'll see that sometimes with the GAN, that basically the GAN ends up just producing the number 1. And then if the GAN is just producing the number 1, then the discriminator is going to give really good values to number 2, because your generator can't produce the number 2. And then suddenly your discriminator goes, hey, 2 is really good, so then it's going to start making a bunch of number 2s. And then once it started making a bunch of number 2s, your discriminator goes, 2 gets really bad results, but no one's made a number 3 yet, so I'm going to give really high value to number 3, and then your discriminator starts moving around. So that's why I brought up the rock, paper, scissors as kind of a good example, that it sounds very simple, but you can get the same effect in a GAN. So yeah, you see that effect in the bottom of the row, and on the top one, you see that it equally actually goes out and covers the space. It doesn't concentrate where you don't want it to. So working off this idea, gradient descent GAN is optimization is locally stable. It's kind of an annoying paper name, but it's an interesting idea, an interesting point. What they do is they try to minimize the original GAN objective as well as the gradient of the discriminator trying to be minimized. So we're going to talk about this for a second, but think about it in terms of what we just saw from the unrolled GAN. So the gradient of your function is, in one sense, which direction you go, but the norm of the gradient is how quickly you go in that direction and how much gain you can get. So if your gradient's near 0, then no matter which way you go, you're not really going to improve very much. If you've got a really big gradient, then you think that moving a little bit is going to make a really big difference to your objective function. It's not necessarily the case. You know, if it is first order linear and it's, you know, if the approximation holds locally, then that is what's going to happen. So what that means is if you're at a point where your discriminator gradient is small, then your discriminator, after a couple steps, isn't really going to do much. If you're in a place where your discriminator has some really large gradient, then your discriminator can do a lot of work and kind of make up for the loss. So what we want to do is we want to update our generator so that our generator improves its loss without giving the discriminator a big gradient. If you give the discriminator a big gradient, you might be doing something for this current step that does really well for you, but the next step, the discriminator is going to be like, I've got a big gradient, I'm going to move over there and make a big difference, and then you've just undone all the work you just did. So that's kind of a first order way, or I guess second order from what you're actually doing, way of looking at what we just looked at. So instead of actually doing those steps of gradient descent, what you can do is you can just look at the next step of gradient descent and say, hey, if I make my gradients really big, then those steps of gradient descent are going to make a big difference. You don't need to actually do the steps of gradient descent to see what's going to happen, to see if you're going to have a good loss. You can just approximate that by saying if the gradient's big, then it's probably going to hurt me. If it's not big, then it's probably not going to be too bad. So we add a regularization term on the gradients, and you'll see, as I was just mentioning, this is another paper where they basically concluded that this is an important thing to do when you're updating the generator, to have the generator also minimize the norm of the discriminator. They didn't really see a great benefit from when you train the discriminator to minimize the norm of the generator, which I guess makes sense, which is you want your generator to confuse the discriminator. That's the place where you want to go. You want the generator to get better and better and better until the discriminator can't tell the difference. If you're going the other way, you're saying the discriminator should get better in such a way that the generator can't get better. So you definitely don't want to minimize your generator weights, your generator gradient. If your generator gradient is minimized, which would have happened if you did it the other way, then you're basically saying your generator can't go anywhere and you're not learning anything. So you want your generator to have gradients, but you just want to get to a point where your discriminator gradients are being minimized, which means everything's kind of evened. You can't tell the difference. And then continuing on this path, this is actually a CMU paper, I believe. I don't remember the authors though. But how to train your dragon, I always include that because I like the name, it's kind of cool. But their idea is to minimize the norm of the gradient in a region around the real data. So minimizing the norm of a gradient makes a function smooth. And if you say the gradient's minimized, that's actually another reason to mention that this is important. Something's smooth if you minimize the norm of the gradient. If the gradient's small, that means it's nice and flat, it's not like a peak. So you don't want to have a discriminator that is just like peaks at each of the real data and nothing else in between. Because if you just got peaks at all the real data and nothing in between, and your generator is over here, then it's got nothing to look at, it's got nothing to do, it's nowhere near the peak, so it doesn't see anything. So what How to Train Your Dragon says is we're going to take some random samples in a space around the real data points, and we want that space to be smooth. So there are two ways it's kind of smoothing. It's minimizing the gradients so that the discriminator itself is smooth, and it's also doing that in a region so that it's not just smooth here, but it's smooth in some ball around it. Okay, so I think those three-ish kind of cover the same general idea, and we'll come back to what the trends are. But these would all fit into the category of, I guess, smoothness and trying to even it out. Yes?
So will this slow down your training progress because essentially you're just trying to make your gradient become smaller?
Well, it slows down in one sense, but if you're saying it wouldn't converge otherwise, or it speeds it up. So a lot of these methods, they have costs and benefits. It's like, maybe a good example to compare it to is something like batch norm, which is like, taking the data and like calculating some statistics on an entire batch takes a lot of extra computation, but if it ends up that it converges faster, then you're good. So that's kind of the same extent, like it does flatten things out, which you would think would make things, you know, converge a little slower, but the other problem is they might have been too steep was actually your problem. So like you're trying to get them to a good balance. Like this isn't going to make your gradients go to 0, but your problems might have been that around them they're so steep that they just make this little peak, and then the peak, if you're not near the peak, you don't see anything.
This is also done just with the discriminator.
Yes, this is another place where we see the discriminator gradients are tried to make nice and flat versus the generator they're not really touching in this particular case, which is an interesting trend. Anyways, so the numerics of GANs now kind of analyze this more to completion. This is a very, very useful paper actually, but they look at it overall. There is a joint vector field of generator and discriminator parameters, and they analyze it as just the total space of here are my generator and discriminator parameters, and how does that point move overall. So not just the independent players, how does that point move? So when is that point stationary? That point is stationary when the gradients of each one are 0. So you've got a stationary point when the gradient of the discriminator with respect to the discriminator loss is 0, and the gradient of the generator with respect to the generator loss is 0. So if you want this joint point to get to a stationary point, then you should minimize the norm of the gradients. So they basically add a regularization parameter, which they call their consensus objective. But their consensus objective is basically saying, let's get to this neutral point. And in this case, they actually do apply it to both generator and discriminator, which we didn't see in the previous papers. So what that actually looks like, first, why do they call it consensus? The generator tries to minimize the gradient of the discriminator loss with respect to the discriminator. And the discriminator tries to minimize the gradient of the generator loss with respect to the generator. So it's not just each guy flattening itself out, they're trying to help each other out. They're both trying to get to a point that is stationary, that has a minimum. It's kind of like a mutual de-escalation. It's consensus. It's all happy. But keep in mind, if you're doing this, that's not just minima. If you say the gradient's 0, what does that mean? It means, I don't know, it's a maxima, it's a minima, it's a saddle point. It could be a lot of things that aren't what you want. So what the consensus term does is it encourages your GAN to go towards minima, maxima, saddle points, and other stationary points, other critical points, but it doesn't necessarily help towards the minima, but it does give it this stability that if the place is going towards, if it's near a minima, it's going to go down to it. So you have to have a small regularization parameter. If you regularize it too much for consensus, then it's going to go to a maxima, not a minima. Like that's not what you want at all. But having a little bit of the consensus can help smooth things out. If you had something that was a cycle and the vector field looked like a circle, now you can make that circle a little bit more like a spiral. You can have it actually go towards the center because you're adding this little bit of regularization towards the center. And here's what it looks like. We have what they call the non-conservative field V, and that is your original GAN. And if you look at that GAN and what the vector field of that GAN is, you see these equilibria that are labeled and these saddle points that are labeled. And those are places where the gradient's 0. Yes, the gradient's 0 there. But if you look around them, the gradients are making a circle. The gradients aren't pointing towards the place that's 0. Like there is a place that's 0, but this is the graphical description of what we were talking about before, of stability versus stationary. They're stationary, the gradients are 0, but nothing's pointing towards them, so you're not going to get there. Then over here we have the conservative field, which is the norm of the gradients. When we calculate the norm of the gradients, we have this new set of gradients that are guaranteed to be pointing towards the saddle points, pointing towards the equilibria, pointing towards each of those. And then we can combine both of those to get a field that's mostly like your original, but now it's got these extra things that are helping it go towards those equilibria. So if you were to zoom in and look at those equilibria, here it's more of a circle. Here you've actually got a little bit of a spiral going on. If there you would have just circled around indefinitely, here you actually will eventually converge to where you want to go. So anyways, that's a set of interesting ideas on the regularization of the vector field. But that's not the only kind of approaches people have taken. One of the bigger papers is called Improved Techniques for Training GANs. And this is maybe more representative of some of the types of work people have done, which is just a paper with like 5 different techniques they wanted to try and combine and put them all together, and maybe not necessarily the most theoretically justified, but it's seeing what works, seeing what happens, and presenting some experiments to those effects. So the types of things that they tried doing. One thing is to reimagine what the loss function is. So the loss function we talked about before is binary cross entropy, and your discriminator is trying to say 0 for this guy and 1 for this guy. This paper suggests, why don't we do feature matching, which is you can just produce a vector from your discriminator. Like the important thing about GANs is that they're fighting against each other, and one guy's trying to tell the difference, and one guy's trying to stop the other guy from telling the difference. The fact that it's a 0 and 1 and binary cross entropy and all of that stuff doesn't really matter to what we're trying to accomplish. So if you kind of throw that out the window, what you can do is just have the discriminator produce a vector and have it produce one vector for real data, one vector for fake data, and the L2 difference of those 2 vectors is your loss. And the generator tries to make those vectors really far apart, or the generator tries to make those vectors really close together. The discriminator tries to make those vectors really far apart. Why would we do this? Well, you've got multidimensional vector that you're producing, so you've got nice and wide. You can hopefully get more gradients coming through that way. And also, it's just an L2 difference between 2 things. It doesn't go to infinity when things go to 0. It doesn't squash. It doesn't go back and forth. It's relatively smooth. It's just the squared difference. We're very used to that, and it tends to smooth things out. Another idea they put forward is mini-batch discrimination. That's the idea that your discriminator is trying to tell the difference between 2 distributions. Why does it only look at one sample at a time to tell what distribution it's a part of? You can actually give your GAN multiple samples. You can give it 10 things from batch A, 10 things from batch B, and say, oh, I think that one's real, that one's fake. So this also directly addresses the issue of GANs frequently collapsing to a single point. We saw the mode collapse that happens sometimes in GANs. And by having a GAN look at multiple samples, that discriminator can try to encourage more diversity. It can try to encourage it to spread out over the space. So it's an easier task if you're looking at multiple samples. If you're looking at multiple things, you can tell the difference between 2 distributions much more easily, because just more samples. More samples give you better statistics of anything. That's pretty straightforward, but GANs didn't do that before, and now we can actually try GANs that are looking at multiple inputs. One more idea they put forward was called historical averaging. This is the idea that we have oscillations. Like, let's forget what it is. Like, we have oscillation. Let's dampen the oscillation. Like, you tell me something's oscillating, you can just add a term to reduce oscillations, and why not? Give it a try and see what happens. And they found that adding terms to just try to dampen oscillations make GANs work better. You try to make certain things a little bit slower, certain things a little more regular, and that helps you converge. So the term that they add is basically keep a running average of where the parameters have been, and you add a term that says your new parameters should be close to your old parameters. So you've just got an extra loss, which is the difference between the parameters, and that means over time it should stay near a mean, it should tend towards its mean. Yes?
So this should also solve the rock, paper, scissors game, right?
Yes, that is, yeah. The rock, paper, scissors game is a little bit of a straw man, I think. There are a lot of ways to solve it, but the point is that if you don't do something, you can end up into weird. So yeah, this does reduce your oscillation somewhat. Whether it works perfectly or not, interestingly, a lot of these techniques have not pulled through, but whether that's necessarily because people found they didn't work or whether they just found other techniques that they preferred, go figure. But yeah. So this is as I said, it's not a technique specific to GANs. It's just if something's oscillating, you can do this to this. It just happens that GANs do that, so why don't we apply this technique to GANs and see what happens. This is actually another example of a common technique, which is one-sided smoothing, or rather label smoothing. Label smoothing is a great technique. It's not specific to GANs in any way. You guys should do this on homework, whatever, just try it on things. It's handy, it's easy. But basically, if you are learning a distribution and you've got labels and you convert them into one-hots, is how we usually do things. We do cross-entropy, softmax cross-entropy, whatever it is, pick your framework. The thing is, if we use targets that are zeros and ones, then that means that your network is trying to output 0 and 1. And if it's doing that using a softmax or it's doing that using a sigmoid or something, then it's trying to output infinity or negative infinity. It's trying its best. It's never going to do it. It's going to squash. But basically, if you have a neural network of really any type that you're training on some sort of cross-entropy type distribution, when you put your labels in as actually hard zeros and ones, you're asking it to squash, and that tends to generalize worse. So label smoothing is just the idea that instead of 0 and 1, you do epsilon 1 minus epsilon. You just take a tiny bit off so that you don't squash too hard, and that actually ends up softening your function. You're not trying to learn a really hard peak. You can learn something a little softer. Experimentally speaking, they call it one-side label smoothing because they found that smoothing the zeros, smoothing your generated targets hurts your network, but smoothing your real targets makes the network work. So basically, instead of giving 0 and 1 for fake and real, you give 0 and 1 minus epsilon for fake and real. Small change, but in combination with other things, small changes like this actually make a big difference in whether it converges or whether you end up with a mess. Another important technique is virtual batch normalization. This is like 5 techniques off of one paper. It was a bit of just like a grab bag of stuff, but it's interesting to see what they did. But virtual batch normalization is great. It makes things converge faster. Everyone knows that. You've covered in class, I'm sure, before. But it's tricky to do in adversarial training because you do have these 2 different players, you have 2 different networks, and batch normalization can hurt you if applied incorrectly. Basically, if your goal is to apply high values for one and low values for the other, and it's batch normalized, you almost can't get it better. If you imagine that all the real data is at 1 and all of the generated data is at -1, and you try to make them closer together, they spring back out. They're batch normalized, right? If they're at these 2 points and they're scaled out to those 2 points, then you really can't get them to where you want them to be. So what they end up doing is actually using one batch of real data, fixing the statistics based off of just the real data, and then use the batch normalization of real data to batch normalize the fake and the real data. So it's not true batch normalization because you're not actually calculating statistics off of all the data that's going into it, but it did seem to help them converge faster.
So when you're training the discriminator, do you batch real and synthetic data together, or do that separately?
Yeah, I've actually tried that before too. It kind of works, but the problem is if you're batching them, what you need to do is you need to batch. You normally batch normalize 1 and then use that 1 to train both. Because the problem is if you're batching them together, then you can separate things arbitrarily large, and it messes up your regularization entirely. It's like an interesting side effect of batch normalization that people don't think about, which is like you just kind of throw things at a wall. But batch normalization completely undoes like L2 regularization or most types of regularization in the network before. And you really got to think about that for a second when you understand what you're trying to do, what you're trying to regularize where. So when you think about it, batch normalization rescales everything to a set constant, right? And something like L2 regularization on the weights tries to make the weights smaller. But if you're scaling everything out, then who cares that you make the weights smaller? You can make the weights really, really big or really, really small, and you're going to have the same outputs exactly because you're undoing the scaling. So what that ends up meaning is that that batch normalization coming here makes the stuff you did over here to try to regularize it to be smaller kind of irrelevant because you're scaling it back out regardless of how big it is. So things like that have issues. And that's where a lot of the conflict is. I think that's actually a really important set of papers that needs to be done, is that current techniques, people just aren't batch norming on their discriminator because they haven't really figured out how to work yet. They're getting it to work anyways, but just working out the right way to do it would probably make things much better. But the problem has been certain new techniques for regularizing your GAN suddenly don't mean anything at all. So it's like, we'll talk about something like spectral normalization, and you're like, oh, I limited the spectral norm of this layer, but who cares if you're doing batch norm after it? Because no matter what the scale of this guy is, the batch norm puts it back to the same point. So basically, you could make tiny differences or big differences. I'm talking a lot about the batch norm part, but it is kind of harder than it seems initially, because naively you just be like, oh, I've got a batch norm function and I've got a discriminator network. Why don't I put the batch norm function in there and see if it works better? But it actually does tend to mess things up for many reasons. Okay. Another paper, although I forgot, oh no, I do have the site in here. So another paper is called the least squares GAN. This continues to mess with the loss function. So we saw the original loss function is cross entropy, then we saw this feature matching loss. Here we see an L2 loss, least squares GAN. So what they actually do is a little bit of a hybrid in between. They've got a target that they want the generator to hit, and they've got a target that they want the discriminator. That second word should be discriminator. Sorry about that. But basically, instead of saying the generator or the discriminator should say 1 for this guy and 0 for this guy using binary cross entropy, you say 0 for this guy and 1 for this guy using the L2 loss or something else. And that way you don't have a log in there, you don't have the squashing issues, you can just have something linear, but it means that your losses aren't going to go shoot into infinity or bottom out to not really being anything if you're in the wrong region. It's a much smoother shape to have an L2. So that goes with our trend that we're going to see of trying to simplify the loss functions over time. Here's another paper, which is a amortized map inference for image super resolution. It's actually a big paper that covers a lot of different experiments, and it's got some like VAE versus GAN comparisons, a lot of stuff like that. But one of the techniques they put forward is called instance noise. It's going to sound really obvious, but this is the kind of thing we're talking about of small tricks like this actually make a big difference. So what they do is they're just adding some noise to your generated images and your real images. That means your discriminator, instead of learning, here's the value at this point and here's the value at this point, your discriminator is learning, here's the value around this point. Here's the value around this point. So there's another paper in that idea of trying to smooth out your discriminator, learn a softer function that might be more helpful and have some more meaningful things in the region around where you're looking. I'm just going to show it. I'm going to speed through a couple of these because we can get to the more important ones. Energy base takes another step into simplification. They say like no Jensen-Shannon. Like we talked about earlier how when you minimize the binary cross entropy, we can calculate here's what the optimum is. The optimum is the Jensen-Shannon divergence, yada yada. We can do a lot of like probability theory on what it's trying to optimize. Here, they're just going to call it energy. Like, we don't have a name for what this value is. We can't point to it and be like, that's the Jensen-Shannon between these two distributions, and we don't really care. It's a thing we're trying to optimize. So they've taken out all the logs, they've taken out everything. Your discriminator just has some linear outputs, and you're just trying to maximize the linear outputs under the real minus the linear outputs under the fake. It's that simple. But what they do have here is this plus notation that's a rectified linear unit. or I guess not a unit at this point, it's just the ReLU function. But instead of having the expectation of the log of d of x and the expectation of 1 minus the log of d of gz, which you'll see in the original, it's just e of x minus e of dg. Very simple, very simplified. The loss of the generator is just what value does the discriminator output for the generator. It doesn't go through a sigmoid, doesn't go through a log, doesn't do anything. It's just the output of the network, that's your loss, problem solved. Now, it gets simplified one step further when the Wasserstein GAN came out. And this is the one that's probably made the biggest impact in GAN literature. They show that they're trying to solve the Wasserstein Earth mover distance. We'll talk about that in a second, what it actually is. But it's much smoother, it's much simpler. It does require constraining the Lipschitz of the discriminator, but the loss function they end up with is just that. It's what is the discriminator output for your real minus what is your discriminator output for your fake. That's it. Much simplified loss function and still works really well. The hard part about this is that you have to constrain the Lipschitz of the discriminator to 1. But one of the advantages of that is if you can do that, you can't overtrain your discriminator. Because if your discriminator has an upper limit to how complex it is, then you could just train it up to a point and it'll just stay there. It won't keep going because there's an upper bound. And that's tricky to do in practice, but we'll get to that in a second. What is the Wasserstein distance? We talked about Jensen-Shannon earlier. You guys probably know what KL is already. Wasserstein you may or may not know. Wasserstein is the mass times the distance you have to move that mass to go from one distribution to another distribution. It's easy to understand, it's symmetric, keep that in mind, but it is hard to calculate. It's, on one hand, the one that most people, when they see this distance, they're like, that's what I consider distance as a person, as like a lay person, that's what I think of. But in terms of actually figuring out what it is and giving a value, that's tricky. So just like a physical example, you've got some products, those products are at some warehouses, you've got this distribution of your products over warehouses, you want to make it this other distribution of products over warehouses. How do you move products from warehouses that you move products the least? So if we were to say, I got to move 5 things from Phoenix to wherever 300 miles away, then you would get 5 times 300 loss for that. So in order to figure out what the Wasserstein distance is, it's what's the shortest way to move these things around. And when I describe that problem as you've got products here, you've got to move them the shortest distance to make products there, you start thinking like traveling salesman, all these like NP hard, whatever. It's actually called the optimal transport problem. The way you move these things is called the transport plan, and that is an NP hard problem. It's what's the shortest way to move everything around. It's very hard to do, but if we could do that, that's our Wasserstein distance. So we're going to compare these metrics. So KL is P log P over Q. Probably seen that 1,000 times. But let's say we've got our real data and our fake data are point masses. So if I've got a point mass at 0 and your generated data is a point mass at theta, what is the KL? So if theta is not equal to 0, then your KL is infinity. So when you look at the equation, log P over Q, if there is a point where P is not 0 and Q is 0, then your KL divergence is infinite. And if theta is equal to 0, meaning the two distributions are exactly the same, then your KL is 0. So if you were to look at the KL divergence between these two distributions, you'd have it's 0 when they're exactly the same, and it's infinite when they're not the same. So that's not differentiable with respect to theta at all. It's not like when the two distributions get closer, the KL smoothly does something. It's infinity all the time until it's 0 when it's perfect. That's not something you can do gradient descent on easily. It's not going to be helpful to you. Jensen-Shannon, not quite as bad, but it still has the same problem. So instead of being infinity, it gives you a log 4, but I mean that's still not helpful. It's always log 4 unless it matches perfectly, in which case it's 0. So that's not differentiable with respect to theta. But Wasserstein distance is the mass times how far you need to move it. So if you want it to be a mass at 0 and it's a mass at theta, then the Earth mover distance is theta. And as the real data gets closer to the fake data, the Earth mover distance goes down. And it goes down actually with this nice just linear absolute value function. So it's differentiable and it's nice and smooth. Let me skip away to this just to visualize that. But here's an example from the paper that they visualize. So on the left, it shows for what we were talking about, as you change that theta, what happens to the Earth mover distance, and it goes smoothly down. This is a function that you can optimize over. And keep in mind, the discriminator is your loss function, right? So like you want a loss you can use. And then on the right, you've got the Jensen-Shannon, and it's like you can't gradient descent to learn that because it's just flat until it's not. Going back a step though, sorry to say over. But what this harkens back to is some earlier results from transport theory, the Kantorovich dual for the Wasserstein distance basically showed that you can calculate what the EM distance is between two distributions by calculating a dual method. The dual method involves learning a supremum over some function. And this starts to get to something that now we can actually approach that with neural networks. We can learn supremums of functions, we can maximize things over functions, and if we can do a maximizing functions problem that actually solves the Earth mover distance, then we're good. The problem with the Earth mover distance is it requires a transport plan. That means each thing over here needs to map to one thing over here. And that's a combinatoric problem. It's one thing here to one thing here. Or maybe it should have been that one to this one and that one to that one. And you can't solve that in a nice convex way. But now with this Kantorovich dual, it's giving us justification that this is a justified GAN. It's not some abstract, we're playing a game and we're trying to confuse people. It's, hey, I can calculate the Earth mover distance and I can minimize that. And if you can minimize the Earth mover distance, then you've got two functions that are matching. So here's kind of a visualization of what it looks like. The red function is what happens when you train, well, I guess I'll start with, on the left, the blue, and on the right, the green, are your real and your fake data.
Going back to the previous slide, how do you differentiate the supremum?
Which one here?
If you're using the dual, how do you differentiate the supremum?
We don't use exactly this formulation, but basically you're just, this psi and this phi are two functions, and you're just trying to maximize the function. Now, whether gradient descent on a function finds the supremum, no. And the other thing is this dual holds if it's over all functions, phi and psi, that this thing at the bottom, it's a little weirdly worded, but it's basically saying there's a Lipschitz constraint. So the C they call there, this is actually the Wikipedia official, like this isn't from GAN literature, this is from optimal transport literature, but there has to be a metric between your x's and y's, and your difference between your phi's and your psi's and x and y's have to be bounded by that metric. Normally we take that to be L2 or something, but that's another place where the problem happens, is we need to find the supremum over a function space, and those functions have to be Lipschitz constrained. And we can't necessarily perfectly solve that, but we can do gradient descent to try to find a local supremum, or local maximum, I guess you would call it at that point. And we can do some other things we're going to talk about to try to make them Lipschitz constrained. But both of those things are still kind of NP problems and a whole other set of headaches. But converting it from one problem to a slightly simpler problem, we can try to approach it. So here we have a comparison of if these are your real data, this is your fake data. If you were to train the original GAN, you would end up with that red line. So we see the discriminator, yes, the discriminator goes up on, it's giving you a 1 for the blue and it's giving you a 0 for the green, but it's completely flat and then it's vertical and then it's flat. That's not a function you want to learn easily. Versus the blue is the WGAN critic. So the function is trying to learn basically the same thing, but now that function has an upper bound on its Lipschitz constraint. it can't go vertically like that because that's an infinite Lipschitz. What it actually has is it has this nice smooth curve because it's bounded, and suddenly if you move around that curve, that looks like something you can use. You can gradient along that curve. But anyways, as I alluded to, what's the catch? One of the biggest problems is now you have to say what's the Lipschitz of a neural network. And that problem by itself is like ridiculously hard because it means, the gradient at every single point in your neural network, which is some complicated neural network, needs to be equal to or less than some function. And that's like, it's not feasible, but there are ways we can try to approach it. But basically, you can't calculate, the Lipschitz is d of x minus d of y. What's the norm of that? Minus the norm of x minus y. So it's an upper bound. It's an upper bound on what's the difference in your output given the difference in your input. And kind of at its limit, you can look at it as just the gradients being upper bounded by some value. And by the way, the original paper really likes to go for the L1 Lipschitz, but there are variations of this where L2, L1, whatever. But anyways, so the way this original paper tries to address this problem of the Lipschitz constraint is it says, let's just clip the weights. Like, if none of our weights are bigger than 0.05, then we know that our Lipschitz constraint is some upper bound. You don't know really exactly what it is, but you're like, it's upper bounded, that's good enough. Practically speaking, this doesn't actually work. So this is a really interesting example of a paper where their theoretical backings of like EM versus Jensen-Shannon and the dual method and like why it works are really great. But what they actually do was like terrible and immediately like, like you guys had great ideas, but the way you executed them didn't end up working. The problem is that they just clip the weights, and if you just clip the weights, then your function has all kinds of weird artifacting, and it just doesn't end up learning anything useful. And the response to that is the Wasserstein-GAN gradient penalty from a paper called, I think, Improved Training of Wasserstein-GANs. So they basically talk about Wasserstein-GAN was a great idea, but the gradient clipping part of it was a terrible idea. The original authors admit that, but it's fine because they came up with the idea, so good for them. But what their gradient penalty alternative idea is, the Lipschitz should be 1 almost everywhere. The gradient should be about 1 almost everywhere. So what you want to do is you want to learn a function as a GAN function, and you also want to say, everywhere I look, the gradient should be 1. Now, you can't calculate the gradients everywhere, so you just have to do samples. And they say, you know what, let's just try that. So what they do is they just take sample points, and they calculate what's the gradient at those sample points, and then what's the square between that gradient and 1. And that's the term you see there at the bottom. It's just calculating over all these points, what's the gradient minus 1 squared. So if the gradient's near 1 almost everywhere, then you've got a 1 Lipschitz function. And if the gradient's significantly larger or smaller, then it's not 1 Lipschitz. This doesn't constrain it to a 1, but it regularizes it towards a 1. And if you regularize it large enough, you hope that it gets to where you want it to be. Now, the problem here is, where are these samples? What are you supposed to do? How do you pick these points out? You can't sample it everywhere, of course. You can only sample in relevant points. And it's finite how many samples you can take. So the bright idea they had is to do linear interpolations between your real data and your fake data. So the question is, where do I want to regularize the gradient? Where should it be smooth? Well, it should be smooth between real and fake. If you have a path between real and fake data that's nice and smooth, then that's the part of the space you care about. And if there's something over there that's not near anything, then, who cares? So you can only penalize the gradient at some finite area. You can only sample over some area. You can't sample over all real numbers, right? You can't uniformly sample between negative infinity and infinity. That doesn't work. But if you figure out, hey, my reals are here and my fakes are here, I'm going to randomly sample between these 2 points, then that's a logical guided way to find the places where you want to sample. Then you just do your penalty at that sample. What does that give us? The top is the original Wasserstein GAN, and the bottom is their GAN. And what you see is the artifacting that I mentioned in the Wasserstein GAN is if you do gradient clipping, it only learns straight lines. So you end up with a discriminator that only learns straight lines, and it makes things that come out of it look silly. So you can give it a Swiss roll, which is this nice little spiral, and it learns like boxes that are somewhat near the roll. Versus when we use the Wasserstein GAN with gradient penalty, suddenly our discriminator and our surfaces really start to look like the points. And you know, like in the left, we see circles around the Gaussians instead of some silly box which is roughly aligned with them. So Wasserstein GAN with gradient penalty is one of the more popular methods. It's not exactly like the latest thing to come out, but it has shown a lot of success, relatively easy to implement, and a great starting point at least. Now we're going to talk about a separate approach for bounding the Lipschitz. And this approach is called the spectral normalized GAN. So the spectral norm, we call it the dual of the two norm. It's basically this equation right here. It's supremum over x, the norm of x times a, over just the norm of x. So it's like what it's the largest eigenvalue is what it comes out to. But your spectral norm is what's the biggest thing that the A can do. If your x is in any direction, in what direction will it grow the largest? And then just put a limit on that. So if each layer of your neural network can only increase things by 1, then all of the layers of your neural network together can only increase something by 1. And that's the way the spectral normalized GAN works. We can analytically determine what's an upper bound on a single matrix multiplication, and then we can put an upper bound on the entire chain of matrix multiplications by just multiplying them all together. This does not actually give you the Lipschitz of a function by any stretch, but it does give you an upper bound on the Lipschitz, and that might be good enough for certain purposes. So we can compare that to the previous method. In this method, we're doing sampling to constrain the Lipschitz to an exact value. So we're calculating the Lipschitz of the entire function at certain samples, versus here, we're actually calculating an upper bound on the Lipschitz of the entire space. No sampling required, guaranteed the Lipschitz at any point and anywhere, any part of this function is going to be less than this value, but it's an upper bound and it's not really tight and it might cause some other artifacting. Now for an interesting kind of deviation from these two, the Fisher IPM tries to do something similar but through a different approach. What we have here is we actually scale the difference by the differences right there. So we use how big the generator and the discriminator are and how big their values are to try to scale the difference that we're talking about. And that ends up basically scaling the loss function using the loss function. You don't need to constrain the Lipschitz anymore. But the problem with this and some of the other issues and some of the other methods is you'll see it constrains and it deals with where the function is currently being evaluated. But one of the big problems in GANs is not getting the discriminator at the generated points and the discriminator at the real points to say the right thing. It's getting stuff nearby that to look the right way. It's not just where's this value, where's this value, it's are the gradients and the slopes nearby pointing in the right direction. So the Fisher GAN doesn't necessarily address that issue. Let's go back a second. I did mention the lap GAN in the last class. But I'm just going to mention it again because it kind of builds into our next one. Lap GAN is a way of simplifying things by doing small GANs and chaining together conditional GANs to make slightly larger things, and that's another way to simplify our training. And progressive growing of GANs involves taking a network and building out a curriculum where you deal with slightly harder, slightly larger images, slowly make a bigger network, and end up with your end goal without having to kind of jump into the deep end all at once. So this is what the progressive GAN looks like. in a second. But anyways, so the takeaways here, that's a big stream of ideas and techniques, and there's some that are better than others, but what I really want to get across is the types of things people have tried. Of maybe we smooth that, maybe we smooth this, maybe we try to normalize it this way. Really what it comes down to is you want to limit complexity, and it's still an unsolved issue in machine learning. Is like, what does complexity even mean? How can we limit the complexity of a neural network? What does that entail? When you've got an NP problem, you can only make it into another NP problem, but sometimes that does help. Sometimes there are approximations out of approximations that you can do to actually get to where you want it to be. But there's some methods we talked about, like unrolling and evolving second gradients. The consensus optimization that I mentioned looks really cool on paper, but then you think about it and you're like, I'm minimizing the gradient of a gradient. That means second gradient of a network. That means my GPU just exploded. So like understanding what's actually entailed both on paper and in real life is important. So some of these methods look good, but they're really expensive. Some of them look good, but they're sampling based. When you're doing sampling, the dimensionality really makes a big difference. With high dimension, you just can't sample enough to get anything done. And there's some methods that are bound based. But we saw those bound-based methods. If you have a lower bound, you get artifacting because you're not optimizing the thing you want to optimize. You're optimizing some bound, which doesn't quite work out correctly. So you end up with straight lines when you wanted curves, for example. And the trends to keep in mind: people are working towards regularization, smoothing. How do you take this discriminator and say some area around here should be nice and smooth and meaningful? How do you get them to go towards a consensus, towards a stable region? How do you get them to come to peace, to come to a central point? How do we eliminate nonlinearities? We saw a lot of different ideas, several different ideas on take this loss function, let's get rid of the logs, let's get rid of the squares, let's make everything easier. And probably the hardest one of all is, what is complexity? How do we constrain the discriminator? How do we learn a neural network and say this neural network is not going to get more complicated than X? What does that even mean? And those are the lessons we've learned. Current research, there's tons of GPUs being thrown into this, crazy amounts of time, but the results are amazing. I mean, you can't argue with what comes out to it. So while you might see some papers and say these ideas seem really ad hoc, at the end of the day, you've got a 2,000 size image which looks crystal clear of someone's face, and they must be doing something right. And as these techniques are getting better and better, people are just making bigger models, always pushing the limits. And a lot of it's been on images, but you really will see there are other modalities people are working on, modeling traffic, modeling RL, modeling whatever, and just trying to take that GAN and apply it to different things. Where is it going? Ultimately, your discriminator is calculating a divergence. We know two things. We know neural networks are universal function approximators, and we know loss functions are functions. So we've always been using a loss function that we engineer to train our neural networks. But maybe we can learn our loss function with a neural network and see where that takes us. But how we can understand complexity, how we can constrain neural networks, how we can have them learn a loss function that's meaningful is really the power of it and where the research needs to go to get a full understanding of what these GANs can do. And yeah, got some references. So I guess any big questions about this? We talked about what you can do with the GANs, how you can make things with the GAN, and then today we talked about how to actually get them to work. So
we talked about all these techniques to train GAN. So if I want to try GAN for myself, which technique?
I would say start with Wasserstein GAN or start with spectral normalized GAN. Those two are currently very good, I would say. And if you're just trying something for yourself, I wouldn't try to implement progressive GANs because that's a bunch of adding layers and making some complicated decisions here. But like I said, I don't want to necessarily endorse one thing as the best because any day you could get something better. And it's also, even using one of those, I would say use a Wasserstein GAN, but there's no reason not to do some smoothing in there, add some regularization and stuff like that. But personally, Wasserstein GAN and spectral normalization, I've had good luck with. One problem with spectral normalization is it only works, as defined on a feed-forward neural network. So if you've got a ResNet, it hasn't been expanded yet to work on a ResNet. If you have an LSTM in your network somewhere, it's not going to work on an LSTM. And that's a trend you'll see with like a lot of things in machine learning. There's a stochastic way to do it where you don't need to know what's going on. You just need to make samples. And then there's an analytic way to do it where like you need to know exactly what's going on, have a full understanding of the neural network to actually get it to work. So you can use that as part of your decision-making process.
Are there any GAN architectures to produce text?
Yes, there's a lot of work on text. There are kind of three approaches, I guess. One thing to keep in mind is you can do something like an adversarial autoencoder, which combines like a VAE loss. So there the discriminator is working on the latent space, not on the output space. So you're still doing a GAN for your generative part, but you end up using something like CDC, cross-entropy, whatever, for your actual reconstruction. Then in terms of training GANs for like a true GAN for text, those end up going into reinforcement learning methods, which sound like they would be really hard to do, but there actually has been progress on it. One of the things that came out like 2 years ago maybe was this like Gumbel softmax, categorical softmax paper, and that's enabled things where you would have had to do pure reinforcement learning, which is just like randomly searching and seeing what happens, where you can actually start to get some gradient descent. So there's like there are a couple papers in like Gumbel softmax, reinforcement learning, GAN for text, would be like the keywords. Yeah, so that's what I'm saying. Like, there are a lot of modalities people work on. Text is, and discrete things are much harder in some sense, but there's been some recent progress on text.
I think we're out of time. Let's
Yeah.
thank Ben. Thank you.
Thanks, guys.